I wish I had an A in Banta. I don't like her.
Okay, anyway, you know that I just recorded that, right?
Score up, Miss Banta.
Anyway, all
I
right.
still want an A though, so love you.
Okay, so limits of functions. So I'm going to start. Everything that we're actually doing today is actually having to do with limits and going back over limits to re-emphasize and to concrete the idea of limits. So what we're going to do is we're going to break up. So I'm going to go over like the basic parts here first. Then we're going to break up, do a little group work here, and then we will come back and actually do the next part here. So limits of functions. So basically, on the AP exam, you need to be able to express limits symbolically using correct notations, determine limits expressed symbolically, estimate limits of function, determine limits of function, and deduce and interpret behavior of function using limits. So we're actually trying to hit all these right here in this whole packet. So yes, it's a big packet, so all right, it's one of those things. Get over it. All right. Okay, so I'm going to start right here. So, okay, so it says for a limit to exist, as x approaches some value of c, the limit of the function must be the same regardless if x approaches c from the right or from the left. If c is either a right or left-handed endpoint, we may be able to find a one-sided limit at that point. Now, so for this, what it's actually saying is, for the limit to exist, the limit in actual L, the left hand, so the function as it approaches C, from the left-hand side has to be equal to the function as x approaches C from the right-hand side. They both have to be equal for this to actually work out, to have the limit, which is capital L. Simply we write, instead of writing the left-hand or right-hand version of it, we just write that the limit right here. So this is with no bounds, so no left and right. The limit exists right there. So it's possible for a limit to exist on the left at one point, and the limit from the right to exist at a different point. And if that were true, both these would not be equal, so therefore the limit would not exist at that point C. Okay, so 3 different things. Okay, definition specifies 3 different conditions must be met. Left hand's equal to right hand, that's equal to the limit. Okay, so we're going to evaluate this. So now, as we do this, I have to find my pen. I know one of these has to work. Maybe this one. Nope. Alright, so let's go with, try red today. Actually, no, red's already dead. Green? Nope, green's dead. Blue. Blue is not dead yet. Alright, so we're looking at this 2 from the left-hand side. That's what this is saying. So I'm going to take a look at positive 2. So it's going to be 2 right here. So we're taking the limit. So we're actually looking to see where is this going 2 from the left-hand side. So left-hand side right here. So here's my left. So it's going down to -2 right here. So only from the left, it's going to go to -2. Okay. Now, right here, from the right-hand side, as it goes 2 from the right-hand side, if you notice right here, 2 from the right-hand side, it's going to -1. But if you notice, that's an open dot. That doesn't matter. Open and closed dots don't matter for this sake right here. Because I'm looking for the limit. Like, what is that number going to approach as it's going that way? It's approaching that. So it's going to be approaching -1. So since these two right here, the left hand and the right hand both are not going to be the same, the limit itself is not going to exist. So this right here is not going to exist. So now, what type of discontinuity is that? That's a jump. Remember that? The jump discontinuity? That means that if you're on a roller coaster right here, up, 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 and to go from here to here, it's got to jump. Okay. So that's one way to actually think about it. It's jumping from one thing to the other. If you actually had like a open dot, is that someone that you guys know?
Yep.
No?
It
Yeah.
was.
Yeah,
Okay. All right. Someone help her out, please.
Elizabeth.
Okay.
Grab a packet and scan
Grab
ID.
a packet and scan your ID. I don't have an ID.
Oh, that's you.
That's
Okay, so now,
You're losing.
so now we have that jump discontinuity right there. All right. So right here. So what this is saying, this is the function of this over the interval from -6 to 6. So there's my x values, -6 to +6. Okay, by -4. So down to -4 and up to +4. So these are my windows for this right here. All right. And there we go. Okay. So two-sided limits right here. So now for this one right here, whenever you see something, now, is there, whenever you're looking at something like this, is there some type of domain restriction here? Restrictions on the domain. Is there any values at x which is going to be, you know, either an asymptote or an undefined or some i's? No, there is none. Okay? So whenever you see some type of limit and you're not going to have any restrictions on their domain, you just plug it in. So if I plug this in, it's going to be, okay, 2 to the third power is going to be 8, minus 5 is 3. Right? Hope so. Okay, good. Now, this right here, this one does have a restriction on the domain, doesn't it?
Yeah.
Yes. X cannot be what?
2.
X cannot be 2. But the problem is, am I plugging in 2?
No.
No, so that doesn't matter. So I know right here for this, x cannot equal 2. And so since it cannot equal 2, I could plug in other things. Okay, so I could plug in everything else but 2. So let's plug in -4. So it would be -4 squared is 16 over -4 minus 2, -6, which reduces to -8/3, right? Okay, so now, so for this one right here, this one also has restrictions on my domain, right? So this one right here is going to have restrictions on the domain. I cannot have 0 in the denominator. So to find out where my zeros are in the denominator, I have to do what? That F word, right? Factor that. So I have this pile of pens and none of them work. All right. So right here, so let's go ahead and factor this. So it's going to be x squared minus 5x plus 6. I'm going to go off to the side. X minus 5x plus 6. Scan yourself and grab a packet. All right, so right here. So factor that thing right there. So now what are the factors of 6? That's going to give me -5. It's positive 6. So if it's positive, what has to happen? Both of them are going to be the same signs, right? So if this is positive, that means both of them have the same signs.
-3, -2.
Very good. So it's going to be x minus 3, x minus 2. So on top, see this right here? On top, whenever you see a minus sign, you have a binomial right here. You have a binomial, and I have a minus sign. Always take a look at the numbers that you have in between here. So this is x squared. That's a perfect square, right? Is it 9 a perfect square also?
No.
Yes, 9 is also a perfect square. So what you can do is actually turn this into difference of squares. So I'm going to factor this out to be a difference of squares here. So this is going to be off to the side. So my x squared minus 9 is going to factor into x plus 3, x minus 3. So now let's take a look at what we're going to have here. So it's going to be x plus 3, x minus 3, and on the bottom it's going to be x minus 3, x minus 2. Now, what's up?
Where is the PSAT test?
I think it might be the library.
Okay, thank you.
I think. Okay. All right, so now, because of the denominator right here, what are my restrictions? X cannot equal positive 2 and 3, right? Positive 2 and positive 3. What am I finding the limit at? Okay, I'm finding the limit at 3. So that means that I have to do some finagling with this, because I'm going to have, this is going to give me my zeros in the denominator, so that would end up becoming undefined. But thankfully, I was able to factor this out. Whenever I have something that I can factor, I always want to try and cancel it out, especially if I'm actually using this here, and it's going to be one of the values that is going to give it undefined. So because of this, I know right here. So now, let's take a look at my factors over here. So I have an x minus 3 and an x minus 3 right here, right? So because of that, I could actually cancel those values. So I'm going to cancel those right there. So if I have the same at top and bottom, I can cancel it out. So now I'm going to be looking at the function of x plus 3 over x minus 2. I was able to remove the discontinuity. Okay, you could remove, so it is a removable discontinuity because it makes it discontinuous. I was able to remove it from my function. And now, can I take it to 3? Yes, I can take it to 3 now. So since I can now take it to 3, that means that it's going to be 3 plus 3 is going to give me 6 over 3 minus 2. So my value is just going to be 6. So I have a removable discontinuity. And whenever I remove this right here, what type of hole does it leave? Oh, crap. Oh, yeah. It leaves a hole. Okay, it leaves a hole. So now, up here, we called this one here a jump, right? This one's a jump, and this is going to be your example of a hole. So this isn't actually a graph. I just want to show you. So a hole would be go to here, at that number, like that. So again, if you consider it like a roller coaster, right here, that means that that is not going to be continuous here, right? That is a discontinuity. That is a hole, okay? Again, roller coaster, that is a hole in my track. So just one spot right there, you're like hole in the track. Roller coaster right here, this one's a jump. So if I'm on the roller coaster, you jump from here to here. And a hole is just a hole in the track. Okay? Does that make sense? Is everyone okay there? Okay? All right, so let's take a look at this one right here. So we were able to do this right here. So now we're going to actually take a look at the limits using the calculator for this. So now everyone, could you please scan yourself? Come this way more. We're going to group up anyway. All right, so right there, scan yourself. Take that seat. Okay, so where we're at, you guys, we're going to grab calculator. So look at the number on your desk. Come grab that calculator, please.
I'm 32. Thank you.
What are you doing?
Will be the SAT.
Oh, I think that's library.
Yeah.
Okay. To deliver this, that's what it was. Okay, but I think you're supposed to be in the library.
It was 34. It was 34.
Yeah, that really messed me up so bad. It's actually good. But like, the ending is just, but not that it's bad. It's just that like it makes you like hurt inside.
You ever seen Life Itself?
Like you watch the movie and like you're just like, what the fuck? Why? Like, why? And like you want to cry at things, you don't have enough.
All right, so to the calculators.
Yay.
Now, I'm going to show you guys some tricks to go along with the calculators, and it's going to be very, very helpful. So we're going to start off here. So we already did the problem. So we did the problem algebraically. So I am on my scratch pad right here. So I'm on the scratch pad to this. So now from here, I'm going to enter my function. So it's going to be control divide. It's going to set up my fraction. X squared minus 9 over x squared minus 5x plus 6. All right, so let's go ahead and take a look at that there. Did I type it in correctly?
Yeah.
Okay, good. All right, so that's my F1. So I'm going to go back to my regular scratch pad here. So given the regular scratch pad, now I'm going to show you guys vars, this button right here, vars. So I'm going to take that and it's going to say the function. So sometimes when you're going to have multiple functions, you'll have like 3 or 4 f's right here. So we have the function we're using in F1. So I'm going to hit that one, and then I'm trying to find the limit as it approaches, what, 3?
Yes.
Yeah.
Hit 3, enter, uh-oh, undefined. So we know right there that it's going to be undefined at that point. But now we're going to actually try and build it up so we can try to table this. So we're going to try the limit process as it's approaching from the left-hand side and right-hand side. So from the left-hand side, I'm going to actually go through and let's see. Vars function. So if I'm going from the left-hand side, let's start on the left-hand side of this would be 2, right? Uh-oh. Why doesn't 2 work also? Okay, so it's also one of the places in which that it's going to be undefined, right? So I need a number. Okay, so let's go, but I'm still trying to find close to 3. So I'm not going to use these, right, 2. I'm going to go closer to 3. So I'm going to say vars 2.5. Okay. Okay, that's 11. Now what about the other side? Could I go 3.5 or 4? Let's try that. 3.5. 3.5. Okay, so now the closer I get to 3, the left hand and right hand number should be getting closer and closer together. So if I'm getting closer to 3, let's say 2.9 now. So vars, enter, 2.9. Okay, vars
3.1. Now, so if you notice, the closer I get to this, these numbers are coming closer and closer together. So the left hand is approaching the right hand here. So they're both coming up to be the same here. So let's take a look at, okay, let's go more points. Vars, okay, 2.99. 2.99. Ooh, getting close. The other side, 3.01. Okay, look, it is approaching 6. So if I go far enough out with really close to 3, 2.9999, it's coming up to 6. Bars again, 3.0001. There we go. So the left hand and right hand of these are both approaching 6. So numerically, this is a way of actually doing a table to try to figure out what your limit is going to be. All right, so let's take a look at where we're at here. So I did this on the other page, so we don't have to actually go through and do this. Okay, so let's take a look at one-sided limits now. Okay, at the endpoints, we can only find right-hand limit as x approaches -3, and the left-hand limit as x approaches 8. Now, what that means is, for a limit to exist, so L is equal to the limit as x approaches C from the left hand, which is going to be equal to the limit as x approaches C to the right hand. So the limit's only going to exist, off screen. There we go. All right, so the limit's only going to exist when both those things happen. But now, if we're only talking about one-sided, okay, we're only going to talk about either left hand or right hand. So right here, as the limit of this function approaches from the right-hand side, I have 1, 2, 3. So -3 from the right-hand side, that works because it's continuous from the right-hand side going to the left right here. So it's going to the number -4, right? Hopefully 1, 2, 3, 4. Yeah, -4. Does that make sense? Does anyone actually have questions on that? The difference in between the limits and the one-sided limits? We're okay? All right, so now for the next one right here, so we're looking at 8 from the left side. So that means 8 over here, so I am actually going this way. From the left-hand side, I'm approaching it this way. So it's 1, 2, 3, 4, 5, 6, 7, 8. It's approaching right here from this, so that would actually give me, let me see, -1, 2, 3. So -3 is that point right there. And it's approaching from the left-hand side. I know it's kind of awkward because it's the right hand of the graph, but it's approaching from the left-hand side. That is kind of awkward. So you have to just read it as, okay, here, now the left side of this is only going to this right here. Now, let's take a look at one more thing right here. So what would be the limit at 5? It's going to be 2, right? So the left hand and right hand both go to the same number. So the limit as x approaches 5 of f of x would be just 2. Does that make sense? Did I confuse anyone yet? Not yet? Okay, I'll keep trying. Limits involving infinity. Okay, now, so for these things, we're actually trying to figure out what is happening to these right here. Now, involving infinity means what is its behavior. The limit is not actually going to exist. infinity is not a number. It is an idea. So if it's not going to a number, it's not going to exist. But it is going to go to a behavior. It's asking what is it doing. So it's going to infinity, positive or negative infinity. Okay? So let's take a look at this. So now the limit as x approaches -1 from the left-hand side. Here's -1. Left-hand side right here. So I'm following it from the left, and this one's going down, and it's going down to that asymptote. We know an asymptote is the MC hammer of math, right? Because can't touch this.
Monday.
All right, so I don't know. Someone left it on my desk. Probably leftover lunch from last week. All right, so this right here is approaching negative infinity. So that is approaching negative infinity. Now, let's take a look at -1 from the right-hand side. Here's -1 right here, and from the right-hand side, this piece right here is actually going up, isn't it? So that means that is going up to positive infinity. That one's going up to a positive infinity. Now, the limit as x approaches 2 from the left-hand side. All right, so now we have 2. Let's take a look. So 2 is right here. Left-hand side is going to what? It's going up, isn't it? It's going up to that asymptote, so that's going to be a positive infinity. Now, 2 from the right-hand side. Here's the right-hand side. Right? Okay, from the right-hand side here, let's take a look. That's going down to negative infinity. Alright, so now these next two things, behavior of a graph is actually hard to read on a graph, especially if you're trying to go up to infinity. So you're like looking at this, you're like, is the gap staying the same? Is it coming up to some fraction of a number? Right? When you look at these, that's the type of things that you're going to see. If you could take it out far enough, you could see what is happening. Okay, I'm going to show you this mathematically though. So if I'm going to plug in infinity, okay, infinity, what's going to happen here? Now, there's a reason why it's going to be 0. Which one races faster? They're both going to infinity, but which one is going to get to infinity faster? The bottom, because the bottom has a higher degree. That means that x squared, so infinity squared is going to be going a whole lot faster than just infinity, right? Okay, so now when the bottom is bigger, it's always going to go to 0. Because if I start thinking about the numbers, the bigger the bottom number, the smaller it is. So if I have like 1/2, okay, then 1/4. The bigger the bottom number, the smaller it is. 1/8. Does that make sense? 1/16. It keeps getting smaller and smaller and smaller because the bottom keeps getting bigger. So as you get so small, it's going to be so tiny that you're going to say that this is going to be 0. It's never actually going to become 0, but it is going to approach 0. It's not going to be 0, but it will approach 0. The limit will be 0. Okay? That means the limit, it's not going to go there, but it will be 0. Okay, so now, let's take a look from the left-hand side. So, from the left-hand side, okay, let's see. That means that if I plug in negative infinity here, so plug in negative infinity, on the top, what am I going to get? Negative infinity, right? And if I plug in negative infinity in the bottom, positive infinity, right? Okay, so this is going to help me figure out where is it going to end up at. So because of that, that's going to be just going to 0. So From the left-hand side, it's going to be 0. From the right-hand side, it's going to also become 0. So both is going to actually take me into infinity. This is going to be 0. But this is going to 0 faster. Now, this is going to be important when we're actually talking about it when they have the same degrees. When they have the same degrees, I have to consider where's it going to end up at if I'm considering the left hand versus the right hand. It's possible for my two sides, if it's going to negative infinity, to be different than what it would be going to positive infinity. Okay, so right here, limit the line as asymptote, graph a function. Okay, positive infinity, negative infinity, B is a horizontal asymptote. Okay, so yeah, all the good stuff. Okay, squeeze theorem. Squeeze theorem is we're trying to actually find this value here, but we can't find it because it is oscillating. Oscillating means that it is going up and down, and as you zoom in more and more, you're still going to see that same behavior. You can keep zooming in as much as you want, but the problem is that behavior is still going to oscillate so much that eventually your screen will just be black. Because it's oscillating, you're never really going to see what it's going to be. Because it's going to approach both sides, and it's going to be away from both sides. So we're trying to squeeze it in between two limits right here. For all x where it's not, not equal to c in some interval about c. So we're taking the limit as g of x from c is equal to h of x, okay? So we're actually getting the limit from the left hand, the right hand, to approximate the limit for the middle. So that's what this means. This is the limit from the left and the limit from the right. As we get closer and closer, we'll eventually come down to the limit of what's in the middle. And that's what we get there. Okay, so here's an example of this right here using the graph. So now this is my function, so this is oscillating here. So it will oscillate to here and here. So we have two functions that are going to represent this. So limit as it's approaching here, okay, and as it's approaching here from both sides. I'm eventually going to end up with 2 for this one right here. So it's both going to come up to 2 because that's what we're going to get. But I'm going to show you guys how to do the math on this one here. Alright. So now, squeeze theorem, we know that sine of x, this is important here. Oh, dang it. I highlighted the wrong spot. This is so important. It is going to be used so often when you see it on the AP test. So I'm going to use this information to find this. Okay, and I'm going to use some. I had scratch paper here. I don't know what happened to it. I know my desk is a mess. Okay, so let's see. Wait, is that it? That's one of them. Alright, so we have tangent as x approaches 0 of tangent 3x over 2x. Alright, so now I like working this out because I hate trying to read what they do because it really doesn't have an explanation. You can't say, hey, what was that? Now, we know tangent is actually broken up of a ratio of sine to cosine, right? That guy, say yes.
Yes.
Thank you. So we could break this up as sine over cosine, but it's the sine of this value, right? So I'm going to be taking the limit as x approaches 0. We have sine of 3x over cosine of 3x times 1 over 2x. Can someone go check to see if that was the door? Someone's beating on the door. Okay, thank you. Alright, thank you. Alright, so now for this right here, we know that I have sine of ax over ax is equal to 1 when I'm taking the limit as x approaches 0. Now, why can I not just plug in 0 here? I can't. Chair's still there? Oh, okay. No. Denominator. What's wrong with my denominator here? Cannot be 0. Can I plug in 0? Say no.
No.
No, you can't plug in 0 here because that would actually give you 0 in the denominator, so therefore it would be undefined. This right here is already been solved, so it is an identity for you. You don't have to go through and do the proof for this. This one always is this. So we're going to go through and actually find this information given that. But for this to happen, what is inside this right here, my angle that is inside the sine, a of x has to be the same as what's on the bottom. In this case right here, is that the case? Say no. No. It's not the case, so I need to manipulate this so it's going to be like that. So I'm going to rewrite this so it's going to be the limit as x approaches 0, and it's going to be sine of 3x over 2x times 1 over cosine of 3x. Okay, they're multiplying together, so I just switch the orders here, so it's going to be fine. Now, I don't want the 2 in the bottom, right? Say yes. Okay, so if I don't want the 2 in the bottom, I have to get rid of it. So how would I get rid of it? Right? I have to get rid of it, and I need to replace it with a what? 3. So I'm going to multiply this by 3 over 3. Since I'm multiplying by 3 over 3, is that going to change the value of my function? No, it's not changing the value because I'm multiplying it by 1. 3 divided by 3 gives me 1. So that means that every time I do this, I'm just changing the way it looks, not changing the value. Now, because this is all being multiplied, I'm going to manipulate this. So instead of multiplying the 2 here, I'm going to change this out. So it's going to be the right here. So I'm going to have 3 sine 3x over 2 times 3x. So it's the same thing. I'm just changing the order that I'm multiplying, right? Times 1 over cosine of 3x. Again, this is my limit as x approaches 0. Now, because I was able to actually move this around, manipulate it a little bit, now do I have my sine of ax over ax? I do. So that's going to be this right here. So it's going to be sine of 3x over 3x. So all that value, I'm going to replace it with 1. Anything times 1 is the same thing, right? No, not anything times 1 is 1. It's the same thing, so I'm not changing it. Like 5 times 1 is just 5. X times 1 is just x, right? Okay, good. All right. So now, since I'm going to replace that, that's now going to say the limit as x approaches 0. I have 3 over 2 because I replaced that, right? So this times this is just going to give me that, right? I have my 3 over 2 times my 1 over cosine of 3x. Okay, so now I can try and do this. If we're trying to do this now, let's see what we got. So I'm gonna plug in 0 for my x value. So 3 times 0 is 0. So cosine, unit circle, cosine at 0 is 1. So if you guys remember unit circles, the circle thing, bam, here, this right here is my 0. That is going to be 1 comma 0. So I have that right there. So the cosine, which is my x value, is going to be 1. So this whole thing is going to be 1, right? So I'm going to have 1 over 1 times 3 over 2. So now, as I did that, my answer is just going to come out to be 3 over 2. Questions before I actually go on? Anyone? Don't be afraid to ask. We're going to be doing this, group work here in a minute. Yes?
Yeah.
Go ahead, speak.
No, I got it.
You got it? Excellent. All right, so let's take a look at the additional practice. That's what we're going to go on right now. So I'm not too worried about the squeeze theorem problem right there. Let's take a look at the additional practice. So this is what I'm going to have you guys do. So we have a number of people here now. So I'm going to group you guys up. I have 2, 4, 6 boards. So there's going to be 6 groups. Hopefully you guys can evenly distribute you guys. So if you want to, like, yes, I'm saying, partners. Yes, you have to go in like, hey, you, my friend. Hey, yeah, you're my partner. Yeah, I say partners, everyone stares at their friend. Ha! Yeah, that's us. Anyway, all right. Okay, so now we're going to do the additional practice. There is 1 through 10, 12. 1 through 12. And I said, yep. All right, so, yep, let's do it. All right, so I'm going to pause this right now.